All right, so I'm going to invite Anna Gilbert. Introduce Anna Gilbert. Absolutely our pleasure to have her as the final keynote speaker of this Missing Data workshop. Anna is the John C. Malone Professor of Mathematics and Professor of Statistics and Data Science at Yale University. Before that, she worked first at AT&T Labs, but then was my colleague as the Herman H. Goldstein Collegiate Professor of Mathematics at Michigan. She has received many awards, including the Sloan Fellowship, and one that I think is particularly appropriate, which was the Siam Ralph E. Kleinman Prize. That is for outstanding research that bridges the gap between mathematics and applications. We're very happy to have you here today, Anna, and looking forward to your presentation.
All right, great. Thank you. It is a pleasure to be here, although I would have preferred to be at IAS, but here we all are. Yes, at Michigan, I was also in EECS with Laura as a 0% appointment. That was fun. So today I'm going to talk about sparse, a problem that I'm calling sparse metric repair, and I'm going to talk about the kernel of the idea and then various applications. I know that you've heard from one of my students and one of my collaborators on this project already earlier in the week, Rishi Santalia. So there's going to be a little bit of overlap with what he did and what I'm going to talk about, but I hope to give you guys an idea of the context of manifold repair and the context of missing data. So this is also joint work with Lalit Jain. He was also at the University of Michigan and is now at the University of Washington, and then with three folks who are at UT Dallas. Okay, so the idea that I sort of started with in thinking about this family of problems is the idea that when you're given data, it's often the case that your data are corrupted in some way, and they're often one of the forms of distortion is in the geometry amongst the data points, or it's not really clear what is the right way to compute distances amongst the points, and you can end up with a very distorted view of the data. So, and it leads you to making incorrect judgments, or, to say this more precisely, further downstream machine learning tasks are just wrong because, you think the world is flat, but in reality, it's not. And I know there have been several talks in this workshop on single cell RNA-seq data. And so this is a great example. This is actually what got me started thinking about these problems. So in this case, you have the mathematician's viewpoint of this data is that you have these big matrices. They are number of cells by number of genes, and each entry is sort of the amount of expression or number of times the gene is expressed in each cell, and or frequency counts. And often, 90%, 95% of these matrices, the entries are 0. And so when you use this kind of data to compute what you think are the distances between cells, the values of the distances just don't make any sense because you don't have enough data. And so I wanted to know, well, how does that impact sort of downstream machine learning tasks? And how do we correct for distorted or broken metrics? without necessarily doing data imputation directly. So I wanted to take a different point of view. So I'm going to build up precision in discussing these problems. And so here's a slightly more precise statement of the lovely flat Earth pictures that I gave. So suppose we're given some similarity data, or it's computed on a data set, and these distances amongst the data points are supposed to satisfy a metric. When this is the case, then you can run downstream unsupervised machine learning algorithms quite successfully. Clustering when you have a metric is better than when you don't. Also, sort of more from an algorithmic theoretical point of view, there are lots of approximation algorithms that have much better approximation guarantees when your distances come from a metric, or even when they come from particular kinds of metrics, like the traveling salesman problem. There are specific sort of sub-analyses of when your TSP problem is in a Euclidean space, for example. So traveling salesman, minimum spanning tree, k-medians. There are certainly applications in computer vision, like image retrieval. And then I have highlighted in orange single cell RNA sequencing analysis. So if the world is great, or at least better, when you have data that is consistent with a metric, how do you ensure that when you're given data? So let's try and define what we mean, by repairing a potentially broken metric, or cleaning up the data. So here's the setup. Is there a question? Question or small child? So small child is also okay. So let's suppose that we're given a matrix D, and it is a symmetric matrix full of non-negative entries. It is said to satisfy a metric if all the entries on the diagonal are 0, and if triples of entries in the matrix satisfy the triangle inequality. I'm not saying anything sophisticated yet. Okay, so I could take the condition that that triples satisfy triangle inequality and rewrite all of those conditions as a big system of inequalities. So I'm going to take my matrix D, and I'm gonna stretch it out and turn it into a vector. So that's what vec of D means. And I'm going to take M. It's going to be a big matrix, and each row of M is going to correspond to a triangle, I, J, and K. And I'm going to call this matrix the triangle inequality matrix. It's got, on any given row, it's got 2 1s and 1 -1. And it's such that the product of M times the vectorized form of D should be entry-wise greater than or equal to 0. That's just a linear algebraic way of specifying, all the entries of the matrix need to satisfy a triangle inequality. Okay, so formally, here's our problem statement for metric repair. So here we're given a corrupted metric D prime. You know that some triangle inequality is broken, perhaps a large number of them, and you want to find a perturbation so that the perturbation of the corrupted metric status is itself a metric. So you want to find a correction or a repair P, so that the new distances adhere to a metric. So here D prime is the corruption and P is the repair. Okay, so there are a surprisingly large number of traditional techniques for solving this problem, although it wasn't called metric repair necessarily, but this problem sort of arises or has arisen in a number of different areas. And sort of, if you will, going backwards chronologically in history, the most recent one, a sort of nearest metric problem studied by Brickell et al. And they said, look, let us find the closest metric to the corruption, closest in some Frobenius norm, or closest in the matrix Frobenius norm. And they came up with an optimization algorithm for doing this. This is like, you could also say, you know, I don't really want such a generic metric. I actually want a metric that is a Euclidean one. Or so you could say, look, let me project onto the cone of Euclidean matrices, and then your objective function looks slightly different because your constraint is slightly different over here. And this has a long history in the psychometric literature, and it is an element that's in multidimensional scaling, which I think is an algorithm that dates to the 60s. There is actually I guess this is not chronological order. There is actually a randomized algorithm for doing metric repair in R3. And it's kind of an unusual thing. It's due to Berger et al. From 1999. It's kind of a cute example. You know, you could also argue that rigidity theory and missing Euclidean distances has a long history in geometry and goes back to the 1800s and to Cauchy, and it's things like, you know, how much can you distort various polygons in the plane and have them remain sort of you know, with desired geometric properties. Okay, so these are all reasonable solution methods for cooking up a good perturbation of the distances. The problem is that they perturb a lot of the distances. And in particular, they perturb, they might perturb ones that aren't broken. And we actually want to take a more optimistic approach and assume that a lot of the distances are actually correct. And only a few of them are correct. Somebody is doing a chat, but I can't really see it. Okay. So
Sorry. I'll tell you. Oh, go ahead, Bianca.
So we do have a question from the chat. Boaz is asking, is there a unique solution to the projection? And if not, do you have any other criteria? I think it was from the previous slide.
Well, so with the EDM, with the Euclidean distance matrices, so it's a question of, are you, you know, are you trying to reconstruct the Euclidean metric, or are you trying to reconstruct the point configuration? So MDS actually comes up with a point configuration, and that isn't unique up to affine translations. And I think these projections are unique, but the projection onto the matrix of distances. But strictly speaking, MDS is a point configuration. It is derived from the matrix of distances, and that is not unique up to affine transformations. Okay. Okay, so what we want to do is find the perturbation that makes the fewest changes to the distances. So, you know, I'm going to write this like a sparse approximation problem. I want to minimize the L0 norm of my perturbation subject to the perturbation corrects the distances to a metric. Okay, and you know, those of you with extensive experience in compressive sensing and sparse signal recovery will say, oh, I know how to solve these problems. I just turn this L0 norm into an L1 norm and go, I'm done. And I will tell you that actually it doesn't work. And it doesn't work for a bunch of reasons. So I can tell you that if you try and do this naively, it won't work. Okay, so it doesn't work because this is not the setup of a standard compressed sensing problem. This matrix M is tall and thin. It's not short and fat. It has horrible coherence. It's just not a good situation. There are more sophisticated sort of L1 regularization type algorithms that work in practice. But I actually want to discuss more of the algorithmic and combinatorial features of this problem rather than, hey, the following heuristic produces really good answers on certain kinds of data. Okay, so let's go look at these convex methods for solving these problems. Well, one problem right off the bat is that there are an awful lot of constraints. There are like n-cubed constraints that come from each triangle inequality. And these inequality constraints make solving large linear programs expensive. More aesthetically or more sort of mathematically, we want to know, sort of what's going on combinatorially in these problems. I mean, they really are quite combinatorial in nature. And, what kind of algorithmic guarantees might we possibly hope for? So is it possible to answer an easier question like, could we even efficiently detect or answer yes or no whether or not the input matrix is even a metric? Can we find broken triangles quickly? And never mind, repair them sparsely. And the answer is probably not. So small children and dogs, hey buddy. So there's a result from 2010, a very lovely result by Williams and Williams that says the following weighted graph problems either all have truly subcubic algorithms or none of them do. So the first one is the all pairs shortest path problem. The second one is checking whether a given matrix defines a metric. So that's the one we're interested in, and then verifying the correctness of the matrix product over the min plus semi-ring. Hey, okay, so can you guys see my pointer? So this problem in the middle,
Yes, we can.
Is the one that we're interested in, checking whether a given matrix defines a metric. And it's interesting because this result is interesting because it says checking a metric is somehow related to the all pair shortest path problem. Okay, so this result gives us a some bad news in that whatever algorithm we come up with, we probably can't do better than cubic running time. But it does give us some good news in that it says this problem is related to the all pair shortest path problem. So let's go investigate this connection more. Okay, and to understand that relationship, let's do some simple examples and observe that we have really different kinds of problems depending on whether or not our perturbation is constrained to be positive or negative. In other words, whether or not we allow ourselves to only decrease distances to correct triangles, or whether we are allowed to only increase distances, or whether we can do anything in between. So I've drawn a triangle. Okay, and 1, 2, and 7, and I've bowed out one of the legs of the triangle and colored it in red. So you guys can see, that 7, it's really too long, okay? It's really too big. So I'm going to consider the problem where I'm allowed only to decrease distances. And so in order to make this triangle look better, the best thing that I should do to decrease, to repair this triangle is decrease 7 to 3. Okay, everybody sees we did that. Notice that 3 is 1 plus 2. Okay, suppose I took a slightly different point of view, and that is I'm going to allow only positive perturbations. In other words, I can only increase distances. So I have my 1, 2, 7 triangle, but this time I've bowed in the one leg because that's the one that is too short, and that's the one I'm going to choose to do the repair on, and the appropriate thing to do is to make it 5. Okay. Notice that the solution that we obtained in the decrease only case is not the same as the solution that we obtained in the increase only case. Okay, over here we changed 7 to 3, and over here we changed 1 to 5. So even for this like incredibly simple one triangle example, it suggests that there's a difference between the problems if we're allowed to only decrease or if we're allowed to only increase. And that we should probably consider these cases for the problems separately. They're really 2 different kinds of problems. Then there's the more general case, general metric repair, where we don't place any restrictions on what the perturbation could be like. We could increase and decrease. Okay, so let's, having divided the world up into 3 kinds of problems, decrease only, metric repair, increase only, and the general case, let's go look at the decrease only case. Okay, and then let us observe. I will tell you that let us observe is a phrase that hides many sins. And I will also tell you that for several months, Lalit and I did not know what to do. And at some point, Lalit came in my office and he said, you know, Anna, I took an undergraduate algorithms class. I think that the Floyd-Warshall algorithm has something to say about decrease only metric repair. And here it is. So it turns out, so I guess I should say, the Floyd-Warshall algorithm is one of the main algorithms that is taught in an undergraduate course, and it is taught to solve all pair shortest path. Okay, so here's the setup. You have an n by n distance matrix D that's corrupted, and you want to find some perturbation P that repairs this matrix D prime. So what do? You run the Floyd-Warshall algorithm on a complete graph with edges given by D prime and the appropriate collection, the appropriate computation of the shortest paths. The distance between the all pair shortest path solution and the weights given by D prime is the perturbation. Okay, so what do? You run through all triangles and you say, you know, look, if one leg of the triangle is greater than or equal to the sum of the other 2 legs, then you should set that long leg equal to the sum of the other 2 short legs. That's the correction. Okay, in particular, this sum of the distances is the shortest path from I to J via K. Okay, so in other words, D hat is the all pair shortest path solution for the complete graph on n points with weights originally given by D prime. And the corruption is simply the distance. Simply the difference between these 2 sets of distances. Okay, that's it. No fancy schmancy optimization necessary. Now you might ask, does that give the sparsest solution? It's certainly a polynomial time algorithm that meets all the cubic, that is consistent with the cubic guarantees of the Williams and Williams result. And it also says, hey, an incredibly well-studied combinatorial problem graph algorithm is at the heart of part of this metric repair stuff. So this slide says, hey, look, if you want to go from I to J, the best thing you should do the best thing you should do is compute the shortest path that goes through K. And so that's how you should repair the metric. Okay, so what kind of guarantees can you get about the sparse problem using this kind of algorithm? And it was actually kind of interesting. Brickell et al. Kind of knew that the Floyd-Warshall algorithm and all pair shortest path was important for nearest metric problems. So they had a lemma that said, if you have the decrease only metric repair problem and d hat is any solution to it, then element wise that solution is smaller than the Floyd-Warshall solution. So somehow like Floyd-Warshall is sort of an upper bound for the solution, but what they didn't have was that it's actually equal. So what Lalit and I showed was that the perturbation that's given by this difference is the sparsest possible decrease only metric repair solution. And in fact, it is the solution to the closest metric in any LP norm. So in particular, it's the closest in like the L1 norm as well. And so what that says is that if you want to find the perturbation that has minimal L1 norm, running all pair shortest path is a way to do it. So this was really cool, except it's kind of at the level of undergraduate algorithms. I mean, it's kind of neat. It's incredibly powerful, but it's only the beginning of the story. Okay, so I said it's only the beginning of the story, and that's because the increase only metric repair problems in the general case are hard, and they require much more sophisticated algorithmic analysis. And once we realized we could solve some of these problems, we realized that the idea of repairing a metric comes up in many different settings.
Anna, we have a question from Laura actually. Is the result for P equal 2, but not for the Frobenius norm?
It is for P equals 2. I'd have to think carefully about the Frobenius norm. I'd have to think carefully about that. I don't want to answer definitively.
Thank you.
I don't know is the answer. Is there another question? I keep seeing things flash here.
No, this was the only question for now.
Okay. Okay, great. So what do I want to say? All right, so the increase only metric repair problem is hard. And Lala and I came up with some heuristics for increase only metric repair that seemed to work okay. Rishi and I could analyze that heuristic and show that in the worst case, it gave like a horrible approximation ratio. So like it's good in practice on certain kinds of data, but not very good in theory. Rishi and I used the sparse metric repair idea to do manifold repair for embeddings. And then Rishi and I also have several papers on using algorithmic tools for solving these large convex programs with lots of inequality constraints to do other kinds of metric learning tasks. And so I'm gonna, I know this is what Rishi talked about. I'm gonna allude to some of that, and I'm gonna walk through pieces of these three extensions. Oh, I should say this work on graph metric repair is with Ben and the folks at UT Dallas. So with graph metric repair, the idea is that we're not gonna constrain ourselves to just looking at the complete graph on endpoints and repairing triangles, but we generalize this to general graphs, and we ask about broken cycles. So the generalization of a triangle is a cycle. And this is the idea that the length of any one edge of the cycle shouldn't dominate the sum of the lengths of the other edges, right? And so in order, that would be the generalization from the triangle inequality. So in order to illustrate that, I've made all these legs 1, and then I've like bowed out this huge leg, it's 10. Okay, there's also the increase only version on graphs where, you know, this edge is too small. It violates the triangle inequality. Here we've got 1 plus epsilon plus 1, which is what, 2 plus epsilon, and that's smaller than 3. And somehow it's tricky to identify that the edge that should be increased is this epsilon here, this one edge. It's tricky because, you know, you might be tempted to increase one of the ones, but that doesn't repair all of the triangles in this example. So I hope this gives you some idea that the increase only case is difficult. I'm going to give you some more intuition about why the increase only metric repair problem is difficult. And that is by going to look at the Floyd-Warshall algorithm. When you have a broken triangle, this leg is greater than the sum of these two legs, and it's easy to figure out which leg to repair. It is the one leg that is larger is the one that you should decrease. But if you have a broken triangle and all you're allowed to do is to increase the sizes of legs, that means that you need to choose one of these two legs to increase. And it's not clear a priori which one you should choose. And in particular, it's not clear which one you should choose so that you don't screw up more things, more triangles later on in your calculation. So I hope that gives you some intuition, that and this picture gives you some intuition as to why increase only metric repair is difficult. Okay, so I'm going to walk through like little vignettes of these 3 problems. Okay, so graph metric repair, this is the formal statement of what I hope was the idea I conveyed to you. So given a weighted underactive graph G, which has vertices, edges, and weights W, and some set omega, which is going to be our set of allowed perturbations. So omega could be, you know, all positive real numbers. Omega could be all negative real numbers. It could be some range. We want to find the smallest set of edges S, such that by modifying the weight of each edge in this set S and modifying it by, you know, pulling some value from this set omega, the new distances satisfy a metric on the graph. And here we, you know, we have this general notion of, you know, cycles as more general than triangles, and you want to make sure that all cycles are consistent with a proper graph metric. Okay, so we have a bunch of kind of algorithmic analysis type results. The first one is not really a surprise given the discussion of the decrease only case. And that is that the decrease only problem is solvable in cubic time. But if you allow the distances to increase even by just single number, so if there's just one number in omega that is greater than 0, this problem becomes NP complete. So increase only metric repair and the general case, they are incredibly fragile. Or maybe I should say the solvability of decrease only metric repair is incredibly fragile. You add one single positive number to this problem and it becomes NP complete. So we did have some polynomial time approximation preserving reductions from some well-studied graph problems, multi-cut and length bounded cut. We also had some approximation algorithms with, with actual guarantees. as opposed to the heuristic that Lalit and I cooked up. These algorithms, you know, the approximation ratios are not fantastic. They're parameterized by, you know, the length of the largest broken cycle is one of them. I think it's parameterized by the size of the sparsest solution. And the running times of the algorithms are just not that great. It's like end of the 6th, end of the 10th. They're just not that good. In practice, they're not as good as the stupid stuff Lalit and I cooked up. I don't know, such is the case with frequently with graph algorithms. So we also have an interesting result which says that if your graph is C-chordal, in other words, if you can come up with you know, chords in the graph, if you can like cut out cycles, and that number is a constant, so it's like some kind of regularity of the graph, then you can come up with a fixed parameter tractable algorithm for solving increase-only metric repair and the general case where the running time of the algorithm depends on this parameter that governs the chordality of the graph. I mean, this is all kind of I haven't written out the full precise statement. It's kind of like saying if your graph is fairly regular, then we can cook up a polynomial time algorithm for solving increase-only metric repair, and the running time depends on this parameter. I have to say, in practice, this is not that illuminating. It's interesting from sort of a graph algorithm point of view. Okay, somebody had a question.
So the question is, do you expect consistency between decreasing and increasing repair? If yes, did you see it in the applications where you had reasonable repairs? What happens if you apply these two methods sequentially, such as first decrease, then increase?
So did we see consistency? So I gotta say, we haven't used any non-heuristic for increase-only metric repair in an application. And I can tell you that when we did kind of simple-minded experiments, I don't think we ran them head-to-head. Like we cooked up random graphs and did, you know, sort of random corruptions. And I don't think we did any head-to-head decrease-only versus increase-only. It is the case that Lalit and I did a bunch of experiments, but it was all for the heuristics for increase-only metric repair, which don't necessarily guarantee anything. So the answer is no, and it's really hard to say. What I will tell you is that simple little 1, 2, 7 triangle I gave you should show you just in a really simple example that you don't necessarily have to have consistency. But, you know, simple examples and worst case gadgets and what happens in practice are all 3 different things. Okay, so this graph metric repair is a slide. It's just a summary of a quite theoretical algorithmic paper, which I think is interesting in its own right, but it's not about applications. So let's go talk about some applications. I know this is what Rishi talked about, and I don't want to step on his toes too much because I know he did a great job. I looked at his slides. But so here's the idea. Here is where missing data and manifolds of data come into play. So many of you are aware that in lots of real applications, it's reasonable to model your real world data as lying on some low dimensional manifold that's embedded in a high dimensional space. And many of the dimension reduction algorithms like isomap, Laplacian eigenmaps, LLE, etc., they all begin by building a graph on the data set using distance information amongst these points, and then using various properties of this graph to compute a low dimensional embedding, and, you know, if you will, unroll this Swiss map, so to speak. Again, this is a bit of a cartoon for how these algorithms actually work, but hopefully you see, we go from here to here to here. And you know what? If the distances on this graph are somehow not correct, then it's entirely possible that this unrolling will be just wrong, will be corrupted, will not give you the correct picture of the data. So in particular, the general, I'm going to do a cartoon of the general structure of these dimension reduction algorithms. Either you're given data and you compute some kind of distance matrix, or you're just given the distances amongst the data points. And you do something like compute a K neighborhood or an epsilon neighborhood, and then, you know, make a graph and do manifold learning of some sort, and then you get a low dimensional representation. Well, what happens if these distances are wrong? And in particular, what happens if you have lots of missing entries in the data, and so your computation of the distance or dissimilarity matrix is not a particularly accurate reflection of the geometry of the data because a lot of entries are missing. So what happens when you run these dimension reduction algorithms on incorrect distances? You know, do you get garbage? And in particular, could you repair this distance matrix so that this flow is better, is more accurate? So we did something kind of funny. We took the Swiss roll data set, that's this thing, and we did the following experiment. So first we took the original data set, and we computed the correct distance matrix, and we ran isomap on it and unrolled it and got this beautiful picture. Then we said, look, let's take the data and let's randomly remove, you know, some fraction of the entries in each data point. So, you know, these are points in 3 dimensions. What if we randomly remove, you know, some coordinates from some of the data points, and then we use that corrupted data set to infer a distance matrix, which will by definition be corrupted because the data are screwed up. And then you use that corrupted distance matrix to run isomap. And you know, I don't know if you guys believe me, but this is the result. That is completely different from this. A whole bunch of points have collapsed on one another. It's not like we got rid of the points. It's that they're all collapsed on top of one another. And so, you know, clearly this is not the right picture for this data set. You know, this is the more correct picture. So we said, okay, what if you took the corrupted distance matrix that you got, that you used to, you know, for this version of isomap? What if you took that corrupted distance matrix and you repaired it using, I think we've used the heuristic for increase only metric repair, and then you ran isomap on the repaired distance matrix. How good a job does it do? And in fact, actually, it's not too bad. You know, you should compare these two things. This picture is clearly not exactly the same as this picture. Somehow we've lost some of these guys over here on the left, these blue dots, but it's not too bad. It's certainly a lot better than this. Okay, so this was like a test example to say, oh, you know, is there something here? So there is something to this procedure, and we ran a bunch of different experiments to evaluate whether or not something was here. I hope you guys got to see Rishi's presentation. Rishi walked through a bunch of these. One of the experiments that we did was just simple visual check. I should also say that these experiments are really and truly computational ones. We don't have a whole lot to say mathematically about, about our heuristics. That is what Rishi and Ben and Greg and I are working on now. So we just did something really simple at first to convince ourselves that, like, if you took a bunch of the MNIST digits and you corrupted them by, like, knocking out 70% of the pixel values in the digits, and then doing our algorithm for correcting the distances amongst these digits, and then embedding with isomap, you can see that, you know, the clusters of the digits are reasonably well preserved. And that's just with 70, you know, with only 30% of the data, with 70% missing. So at least in terms of pictures, isomap is producing pictures after correcting the distances that are reasonable. Okay, this is just a visual verification. Okay, we then said, hey, we could actually quantify how much better these embeddings are after correcting the distances. We can look at how well an SVM trained on the low dimensional projections does for classifying digits. And so I want to give you, these are 4 digits that have been corrupted. You know, they're missing a huge amount of data. And if you correct the distances amongst the data points and then run SVM, you actually do pretty decent as far as classification goes until you're missing, you know, roughly 70 to 80% of the data. Okay, and hopefully, what's funny when I give this talk like on a real computer screen or on a projector is that you can do the following sort of visual experiment. You can go stand on one side of the projector screen, and it's really clear that these digits are 3, 5, 6, and 8 from one direction. And then I was giving this talk somewhere, and somebody in the back of the room who wears glasses said, you know, if I squint or I take my glasses off, you can actually see the digits. And so I had a long discussion as to whether you have to, we had a long discussion about the difference between correcting the data by, like, doing some Gaussian blurring, because that's what you're doing when you're squinting, or correcting the distances amongst the images themselves. And I have to say, I don't really know which works better. This is one of these problems that, follow-up problems that Rishi and I, it's one of a long list of follow-up problems that Rishi and I are working on. I don't know, it's an interesting question. And I kind of wanted to use this example to point out that when you have missing data, you can either try and repair the data or repair some geometric structure on the data. And we went for the latter. And I think it's a fantastic sort of mathematical, algorithmic, geometric question as to what difference it makes, you know, under what conditions. Okay, so let me see, okay, so that's it for that vignette. I want to end with a philosophical discussion, or, you know, to emphasize that philosophical discussion that I was alluding to in the difference between correcting data versus correcting some geometric structure that's sort of inferred or removed from the data. Rishi and I have cooked up a number of algorithms for learning a metric given distance information or similarity information amongst data points. Can you learn an appropriate metric that is consistent with the similarity stuff? And again, taking a different philosophical perspective from sort of standard metric learning ideas. We wanted to learn the right metric on the data, the right geometric combinatorial structure, and then do an embedding of that geometric structure into this two-dimensional space. So rather than, there are a number of techniques that try and do this embedding via optimization directly. And so I think that these two example problems are good examples of, I think, the power of this philosophical approach of compute a combinatorial structure first, and then do some kind of optimization procedure for studying the geometry of data stuff. So thank you. I'm going to stop here and take questions. More questions.
Thank you very much, Anna. If there's any questions for the audience, could you please write them in the chat, or if the panelists have any questions, maybe they can ask them themselves.
Yeah, I have a question and I didn't know how to write it, so let's see if I can say it. So I'll do my video too. So when we're looking for an actual point embedding, like you said, you know, it's never unique, certainly to translation or affine transformation. But it's also not unique in the case that you don't have actual distances, but you just you know, have comparisons, like non-metric ordinal type of information, and then you can kind of jiggle things around a little bit. Usually, I mean, if you have enough points, it's sort of unique-ish, but there's like, you know, a little bit of jiggling you can do and still get something that satisfies all the inequality constraints. Is that similar for the metric? Like, it seems like, you know, there are cases where you could go up, you could go down, or at least some kind of scaling that the two different metrics would be equivalent in some sense.
So yeah, we really haven't looked at that. We haven't looked at that question so much. I mean, right, so inherent in your question are like a whole bunch of really cool ideas. So like one of them is the metric that you repair to, right, so one is the metric that you repair to unique? And the next one is, if you were to have a point set that would instantiate that metric, is the point set unique? And if so, up to, or you know, is it unique? No, but modulo what kinds of geometric transformations?
Right.
Okay, and then you're also asking, and I don't know, for some of those questions, you know, it's known, you know, about Euclidean metrics and these rotations, but for general metrics, I don't really know. And I know that we are currently trying to tease out, you know, if I have a distance matrix and I want to find the closest Euclidean distance matrix to it, sort of how do I do that? What do the algorithms look like? Are things unique? If I perturb my distance matrix a little bit and then ask what is the closest Euclidean distance matrix to that perturbation, how far is that from the original distance matrix?
Mm-hmm.
And I gotta say, those are all fantastic questions. We don't know the answers. There are some really weird phenomena that happen with, like, you know, you get a huge explosion in the rank of the matrix because there are tight bounds on the rank of Euclidean distance matrices for, based on the number of points that you have, but there aren't for general distance matrices. And so, you start out with a low rank matrix, you perturb it a little bit, you repair it, it becomes a huge high rank thing, and then what do? I don't know. These are great questions, Laura.
Yeah.
I look forward to your talk and to Mark's talk.
Thank you.
Are there any other questions for Anna?
Tank, you got a question?
Well, if not, thank you very much for your talk again.